Hello and welcome everyone to the ARPIT course on numerical methods in civil engineering. I am Yogesh Desai from the Department of Civil Engineering, IIT Bombay, and this course will be taken along with me by my colleague Professor Eldo. In order to make these interactions effective, we have planned to deliver the course in the modular form. So, different modules we have in front of us. Module 1 deals with mathematical modeling, Module 2 solution of equations and numerical approximation. Basically, in this module, we will talk about basic concepts and founding blocks which will be later on employing in modules 3, 4 and 5. So, the today's lecture is the first lecture in module 2, that is solution of equations and numerical approximation, and we will start with solution of linear equations. Why we need to study linear equations? On the basis of our understanding of the given physical problem, we first convert it into an equivalent mathematical problem. This equivalent mathematical problem could be in the form of algebraic equations, which could be either just one equation or simultaneous equations, can be linear or nonlinear, and more commonly the mathematical problem of a given physical situation is described in the form of differential equations, which could be either ordinary differential equation or partial differential equation. As the name suggests, we have derivative signs appearing in the equation. And the third category of equations, what we call integral equations, obviously it includes the integration sign, and in addition what we have is the unknown parameter appears within the integration as a part of integrand. So, that is what we mean by integral equations. So, we will be spending some time on these different types of equations as we go along. So, now I start with the algebraic equations, since already we have been studying these linear simultaneous equations. We will quickly review the same and then have a fresh look at these equations from a slightly different perspective. So, we have simultaneous equations of the form matrix K, and for specific purpose in mind, I am talking about a rectangular matrix m rows n columns times the vector of unknowns, that is q, equal to the right hand side quantities which are known to us f. If coefficients of matrix K are constant, then we say we are dealing with linear simultaneous equations. On the other hand, if the coefficients of K are themselves function of Q, which are unknowns, we say we are dealing with nonlinear simultaneous equations. So, let us talk about the linear simultaneous equations. The case that we have been studying most of the time, square matrix m equal to n, and if determinant of K is not 0, we can find unique solution of unknowns Q by using various techniques. So, these techniques we will not be covering as part of this course. So, the learners are requested to study these different techniques like Gauss elimination, Cramer's rule, etc. on their own, so that it will help them in times to come. Here one thing we may like to note, that if determinant of K is 0, basically we talk about rank deficit matrix. One or more rows of the given matrix K are basically formed using linear combination of other rows. Now, when we talk about application of such equations as arising from the mechanics, basically something we have missed out in formulating these equations. If we talk about stiffness method, if K is having determinant value 0, it means we have not constrained our system adequately. In certain nonlinear analysis also, determinant of k can become 0, and this aspect we will examine little bit later. So, now this was the straightforward case of simultaneous equations square matrix. What if we are given rectangular matrix? So, let us look at one such case. When we have number of rows more than the number of columns. What does it mean? We have more number of equations than the number of unknowns. So, in order to find solution of such a system of equations, what we can do on the basis of our past understanding of the problem being investigated, we can eliminate few equations, or somehow we know from our past experience certain equations contain more error. So, those kind of things we would like to eliminate and reduce the number of rows and make them equal to the number of unknowns, thereby converting our matrix to a square matrix. The other more robust technique is what we call application of method of least square. Now, you see, generally we talk about method of least square in the context of curve fitting. The important takeaway from the discussion that we are having now, the concept that we study in certain setting, certain situation, if we understand the concept properly, we can apply it to another completely different situation, thereby making the task on hand extremely easy. So, these mental barriers of using certain technique or concept in the context of certain topic, actually those barriers we should remove, and once we do this successfully, we will be able to better apply the knowledge we acquire while going through different courses, different topics, so on and so forth. So, when we will discuss the application of method of least square to different areas of civil engineering, we will revisit what is being discussed now, but for the purpose of this current discussion, it would be sufficient to say that if we pre-multiply both the sides by k transpose, obviously the left hand side k transpose k will become now a square matrix of size n by n, and as long as m is greater than n and we do not have linearly dependent row, each rows are that way uniquely obtained, we can find approximate solution. Let us examine another case where we have less number of equations than the available unknowns in the equation. Obviously, it is not a magic, we cannot solve such system of equations. We need to generate additional equations if all the unknowns contained in our system are important to us. So, that is the first requirement, and if we are not able to do that, somehow we have to eliminate certain number of unknowns which are less relevant in the context in which the analysis is being done in the case. So, of course, there is some judgment involved here and it is not a straightforward or direct process. So, generally we try to avoid case 3 kind of situations by having adequate number of equations. Now, other point we would like to touch upon here, that generally in an analysis of a structural system, a mechanics related problem, the size of ensuing simultaneous equations would be huge, and many a times it becomes a challenge to handle large number of equations within the available computational resources. So, in that context, now we talk about the concept of static condensation. The idea is we would like to reduce the number of unknowns without introducing any additional approximation into our system. So, in order to understand the concept, let us partition the given huge matrix into subparts. So, in the matrix form we have shown here, where S is the number of what we call as secondary unknowns, P as number of primary unknowns. So, total number of equations N equals S plus P, and the size of these different submatrices we can easily infer from the partition equation that we have in front of us. For example, K11 will have dimension S by S, K22 P by P, K12 S by P. Vector Q1 containing our unknowns is a vector of size S by 1, what we call contains secondary unknowns. Secondary means they are not less important, but we calculate them subsequent to calculation of primary unknowns which are contained in vector Q2. If we talk about on the right hand side quantities, F1 are the terms which are known to us, which are basically appearing in the first S equations, and F2 vector contains terms appearing in the remaining P equations. So, through some matrix manipulation, we will eliminate S number of secondary unknowns and recast the given equation in terms of a subset of size K22, that is P times P, and Q2, those are the unknown parameters we will retain in our solution, and the right hand side vector F2 that will be modified as compared to the given F2 in the process of this matrix manipulation. So, now we have reduced subset, and the size of P by P matrix will be much smaller than N by N, and we can handle this very conveniently within available resources. So, how we do this? So, we expand the partition equations as shown in equation set 1 and equation set 2, and from these two equations, first we eliminate Q1. So, as a result, we have equation in terms of Q2 alone, as we have shown in this equation. Assuming that K11 and the ensuing matrix quantity K22 minus K21 K11 inverse K12 is not having zero determinant, we can solve these equations uniquely. Once we have obtained Q2 from this equation set, we can go back to our equation 1, substitute the value of Q2, and if K11 is invertible, we can compute Q1. Now, the question that may come to our mind, we are still inverting the matrices K11 and the modified K22. However, we realize that compared to N, S and P are much smaller numbers. So, the computational effort required is much less than inversion of the full matrix K, which is of size N by N. So, where we use this static condensation? As we discussed, the first and the foremost application is to reduce number of equations, and this concept we use quite extensively in finite element method when we talk about substructuring. And one classical case of substructuring is soil structure interactions. As we know, soil is a very complicated material. Many times we have to do thorough analysis to study how the loads are transmitted safely to the supporting soil media. And in this context, we need to do soil structure interactions. So, all the degrees of freedom, that is the unknowns pertaining to our superstructure, we condense out and we show them in their equivalent form at the interface of our structure and soil junction. And then we do detailed analysis for the soil mass. We get the parameters of interest and then substitute them back into our earlier equations and recover response of the structure. So, that is where we see very important application of static condensation. Now, modern day finite element based commercial software packages, they talk about unlimited capabilities, unlimited size of matrix that can be solved. Obviously, for such a robust software, we have to use what is called out of core solver. As the name suggests, only a tiny part of the matrix to be solved resides in the CPU of the computer. Remaining parts are written on the auxiliary storage device like hard disk. So, whatever tiny part is contained in CPU of the computer, the processing is done, the process data is written to the hard disk and the next block is read in, that is processed and again that is written back to the hard disk. So, this kind of swapping of data from the hard disk to CPU keeps occurring, and as a result we require lesser CPU memory to solve large system of equations. So, such solvers are called frontal solvers. Essentially, that is the application of Gauss elimination method in the out of core setting. So, these are the applications of static condensation. Let us look at one typical example which would illustrate how we can use this technique. So, we have taken 4 by 4 matrix set x1, x2, x3, x4. These are totally 4 number of unknowns, out of which x1 and x2 we would like to treat as primary unknown. Now, this example we have taken from our book on finite element method with application in engineering, published by Pearson Publishers. In order to use the expressions that we derived, we need to rearrange rows and columns such that the primary unknowns are brought down to vector q2, secondary unknowns, that is in this case x3, x4, we have to push up and bring them to vector q1, and this vector q1 we are going to condense out by using the expressions that we derived just few minutes ago. So, that is what we will do. So, we rearrange the rows and columns, and once we rearrange the rows and columns, we have our submatrices K12, K22, K12, K21 and also the subvectors F1, F2, Q1, Q2 as shown in this slide. We are going to retain Q2 vector, that is what we are calling vector consisting primary unknowns, and we are going to condense out, that is eliminate the components of vector q1 using the expressions that we derived earlier. And once we go through this process, we get our reduced equation as shown here, the modified vector F2, and now this is a 2 by 2 matrix, can be inverted easily, and when we invert K22, basically we will find Q2, and once we find Q2, we can substitute it in the vector Q1 equation, and we get Q1 and Q2 as shown in this figure. Okay. Now, the question is, what are we achieving by doing this? As we can see easily here, we are given 4 by 4 equation. Of course, we can invert it, but that is bit more effort. So, we are basically setting up the equations 2 by 2, and this equation we can actually solve easily, and the solution thus found would be exactly the same as the solution we would have obtained had we solved the given 4 by 4 equation set, and that we can easily verify by substituting Q1 and Q2 in our given equation set and see that it is satisfied identically. Okay. So, that is about the static condensation. We also talked about the application of static condensation. So, what we are going to do in this course, first for 20-25 minutes or so, we will present certain concept, discuss some application part of that, and we will follow it up with assignment, so that you can practice on your own and have better grip of what was discussed. So, that is the style of this delivery we are going to follow for the entire course. So, having said that, I will now talk about the first assignment coming out of the topic that we discussed, treatment of linear equations, and also we would like to talk about little bit fluency with the matrix operations. So, in this context, this assignment number 1 has been prepared. The first question of this assignment, we are given certain matrix quantities K, which is a square matrix, and K equal to K transpose, that is what we mean by square matrix. T is a rectangular matrix and Q is a column vector. We want to compute matrices M1 through M6 appearing in the expressions shown in A through F. So, the idea is to become familiar and fluent with basic matrix operations. Of particular interest is expression for M6. Just think about it for a minute and work out the size of M6. You would have seen such equations in your earlier course on stiffness method. If you recollect, product such as T transpose KT we commonly encounter when we transfer member level contribution in the local direction to the global direction. Okay. So, T in that case would be the transformation matrix and K as the stiffness matrix. Now, when we pre-multiply and post-multiply this T transpose KT with Q transpose and Q respectively, basically we are talking about expression of energy, which is a scalar quantity. So, the dimension of M6 will be 1 by 1. We also need to understand how calculus based operations are performed on a matrix. So, in that context, we have question number 2. We find the derivative of the given matrix, and we do this by taking derivative of each and every term of the given matrix. Similarly, we can talk about integration of a matrix, and in this case each and every term of the given matrix is to be integrated for the range given to us. Now, in order to understand the application of concept of static condensation, question 3 is given to us. We have here 5 by 5 matrix. So, in first case I would like you to find the solution using Gauss elimination algorithm. Okay? So, that is part A. In part A, I would like you to condense out Q2, Q3 and Q5 and recast the equation in terms of Q1 and Q4. So, in this case S is 3, P number of primary unknowns is 2 and you compute the ensuing 2 by 2 matrix to get Q1 and Q4 and ensure that these values are the same as those you have obtained through part A. In part C, what I want you to do is making use of Q1 and Q4 as obtained in part B, again go back to the equations we derived for static condensation, and from Q2 now we will recover the primary unknown set Q1 consisting of Q2, Q3, Q5. And again the secondary unknowns you check with your solution obtained in part A. Okay. So, basically this is what we mean by static condensation. So, with this we will close our discussion related to treatment of simultaneous linear equations. Thank you.